So let's talk more about interpolating functions. So again, we want to have u is approximately equal to u of h is equal to Cj phi j plus phi 0, where phi 0 satisfies the essential BCs. Otherwise, the phis have to satisfy the following. One, phi j must be selected such that B phi I phi j is defined and non-zero. That is, they must have the proper continuity. So in other words, if I have a term in my integral that's like the second derivative of u with respect to x, then I can't choose u of h to be equal to x, right? Because if I take one derivative of u of h and then I have 1, and I take another derivative and it's 0, right? So they have to have enough smoothness such that the result is not non-zero. Okay? Phi j must satisfy the homogeneous form of the specified BCs. So that is, if I have u at 0 is equal to u0, to some number, the phi j must satisfy the homogeneous form u of 0 equals to 0. I've already said this, but I'll just write it down again. So for completeness, the set of phi j need to be linear independent. So phi1, if phi1 is equal to x minus 1 of x, and phi2 is equal to x squared 1 minus x, then phi3 cannot be 2x squared 1 minus x. Right? Because this term is linear independent, or is a linear multiple of the other ones. The set of phi j's must be what we're going to call complete. So, for example, if I choose x, x squared, x cubed, x to the fourth, this is a complete set. If, in 2 dimensions, if I choose x, y, xy, x squared y, x y squared, x squared y squared, this is complete. However, I cannot choose x third, x to the 5th, x to the 25th. This is not complete. Or in 2 dimensions, I couldn't choose x, x squared, xy cubed. This is not complete. So the completeness comes from something called Pascal's triangle, or the way you can determine completeness. And it looks something like this. So you'd have 1 x y, x squared, xy, y squared, x cubed, y cubed, x squared, y, y squared, x, and so on, right? And so, you know, this would be a complete set, or this would be a complete set. But we can't skip around, right? You can't choose x, y, and x squared y. Then, of course, if you have 3 dimensions, then there's like another end of the board. It's a pyramid, you know. Yeah.
So if we go for just 1 x and y, is that transfers
Yeah.
complete?
It's complete. Yep.
If you go for 1 x, x squared, x cubed, and then up.
1x, x squared.
Then the x cubed.
Now, if you went to x cubed, you would have to select all of them.
But is already just like the one, like the x.
No, only the xy, but yeah, it has to be symmetric. You can't,
Oh,
yeah, you can't skew it one dimension. Yeah. And then, so I guess this is 3. Oop. 3. And 4 is, well, phi 0 must be the lowest order function that satisfies the BCs. And I said all that to just finally say we almost always use polynomials. That's not to say that you can't use other functions. You can. You can choose your basis functions to be trig functions, trigonometric functions. You can choose them to be if you want. Sometimes if you happen to know something about the character of the solution, you might choose your basis functions based on that. Like if you know the solution is an exponential, then you could get by with less terms if you chose exponential basis functions, right? But if you don't know what the solution looks like, which is most often the case when we're using the finite element method, the reason we're using the finite element method is because we don't know the solution, right? We're using it to solve it. In those cases, then we almost always use polynomials. So